Right, here I am for homework 4 part B. So for this part, we will be doing an analysis on the transfer function of 3 tanks in series. So to start off, we're going to have our transfer function is k over tau s plus 1 cubed. Right, and so this tau s plus 1 cubed is because there are 3 tanks. Instead of just one, which is what we had in the previous part. Now I'm going to draw a block diagram. So coming out of this will be our final height. But that will go through. We have some measurement system, GM, and then that goes up. We have our set point, and we do our set point minus this measured height, which gives us our error, and then we will multiply that error by GC, which is our controller. Now, this k over tau s plus 1, I'm just going to write in as GP, and then we are going to do an analysis of this block diagram. So coming across the top, we have our error times GC times GP equals our height. That's just multiplying across. Our error equals our set point minus our height times GM. All right. Now I can substitute that in. We have HSP minus HGM times GCGP. So I'm just going to write those in, factor that out now. All right, so we can then add this to both sides and then factor our H. And then lastly, I'm going to divide by this here. So we have H equals GC/GP over 1 plus GM/GC/GP times our times the Laplace transform of our height set point. Now what I'm going to do, I'm just going to say that GM equals 1 and GC is some proportional controller KC. Then I'm going to also substitute our k over tau s plus 1 cubed. So our height is going to equal KCK over tau s plus 1 cubed over 1 plus KCK over tau s plus 1 cubed times our height set point. Now this looks very messy, so I'm just going to multiply everything by tau s plus 1 cubed. So what we get, tau s plus 1 cubed over tau s plus 1 cubed. So we get tau s plus 1 kc over k over tau s plus 1 cubed plus kck times our height set point equals our height. All right. Now, if we imagine we have some time value and our initial height, and then it goes up to some other height, we just have a step function like that. The Laplace transform of that is going to be our h minus h naught over s. And we'll just call this big A. And that is our Laplace transform of our height set point. All right. So A over S. Now I'm going to multiply out this tau s plus 1 cubed. If you remember Pascal's triangle, first order, second order, third order, we have 1, 3, 3, 1. That's just our powers of 11. So bringing it over, we have h equals kck over tau cubed s cubed plus 3 tau squared s squared plus 3 tau s plus 1 plus k times a over s. Right, so now we've taken our function here and separated it out. Now with this, we are able to do our Routh-Hurwitz stability analysis. So we are going to look at the denominator here, and in our inverse Laplace transform, we will end up with e to the negative bt, where b is the negative of our root. Now, if our root is negative, then we are all good. Or if it's 0, then e to the power of that value times t is going to diminish. If our root is positive, then our exponential is just going to grow and grow and grow, meaning that our system is not stable. So the Routh-Hurwitz, of course, we know that this root is 0 already, so we don't have to worry about that. If I take our tau cubed, place it here, and then we have 3 tau squared, 3 tau, and then 1 plus kck, and then a bunch of zeros. What we want to look for is sign changes in this first column. Right, so tau, of course, is always going to be positive. So both of those are positive. We want to look for more positive. Next up, what we want to do is take this bottom left times this top right, times the top left times the bottom right. Sorry, minus the top left times the bottom right, all over this bottom left. And so we'll get 9 tau cubed minus tau cubed of 1 minus 1 minus kck. And then here we have 3 tau squared times 0 minus tau cubed times 0. That's just 0. And then the zeros continue onward. For the next column, what we want is, this is over 3 tau squared. The next column, we want to multiply this bottom left by our 1 plus kck minus 3 tau squared times 0, which of course is 0, and then divide by our big fraction again, which just means we end up with 1 plus kck, and then we have zeros going on, and below that is all 0. So we don't have to worry about anything else. We just need to look at if these two are greater than 0. So we have our, in this one, the denominator is always going to be positive because it's just 3 tau squared, and tau is always positive. So we have 9 tau cubed minus tau cubed times 1 minus kck must be greater than 0. We can immediately take out the tau cubes and then add this 1 minus kck to both sides. So 9 is greater than that. 1 plus kck. 9 is greater than 1 plus kck. Subtract 1, we get 8 is greater than kck. KC is some controller that we are going to set. K is based off of our transfer function. So we will say that 8 over K has to be greater than KCK. That is going to be our limit for that. Then over here we have 1 plus KCK has to be greater than 0. So just subtracting 1 and dividing by K. KC has to be greater than negative 1 over K. And that is our second criteria. So we just know that 8 over K is greater than KC is greater than negative 1 over K. And that is going to be our criteria for stability. Now, to prove this, I'm going to head on over to Python and code this up. Right, here I am in Python, and so what we'll be doing is testing out this Routh-Hurwitz criterion that we just measured for k equals 12 and tau 1.2 with a change in set point of 0.12. I do not want AI. So we'll have k equals 12, tau equals 1.2, a equals 0.12. Now our GP, that's our k over tau times s plus 1 cubed. And our GC, that was what we did the Routh-Hurwitz on, and we said it cannot be anything greater than 8 over k. So 12 over, or 8 over 12 is 2/3. So to start, we'll be doing 2/3 minus 0.1, right? Just so that we know it's within that range. And then G equals GC times GP over 1 plus GC. Oh, that's an exclamation mark. 1 plus GC times GP. And then we'll be doing a simulation that gets us our height and deviation. So equals sim of G. And then we need a function of time. That is our step change. So we'll do a lambda function, and that's just going to return area. We'll do n equals 1000 and dt equals 1. And then we'll make a figure. So fig equals make subplots. Fig dot add scatter. X equals t, y equals h deviation, mode equals lines. And here you can see that this converges, right? So our GC is under under 8 over 12, sorry, 8 over k, so it works. We then just do plus here. We can see it's the opposite, right? It goes off, you know, it keeps growing, and that's when GC is over 8 over k. And I believe the other one was negative 1 over 12 over k. So negative 1 over 12 plus 0.1 should converge, right? Not necessarily a good answer, but it will converge. And then minus 0.1, you can see it's, you know, 10 to the 107. So just absolutely wild numbers, but this shows, you know, this Routh-Hurwitz that we just did showed that it did indeed work. You know, that weird root solver, you know, that only shows if they're all positive or all not positive, you know. It actually does show the maximum and minimum values of KC that we can have. So now I'll be moving on to part C.